Alright guys, so this is going to be your video for your fundamental theorem of calculus. We're going to go over the first and second fundamental theorems. The first one's going to be a review, the second one is new. So here we go. Okay, so here's our little review topic from last week, which is our first part of our fundamental theorem, part 1. And this is for finding a definite integral. We know we have definite integrals when you have upper and lower bounds. And we know that what we do is we take our integral, we plug in our upper bound, and subtract when we plug in our lower bound. So I do want to talk about when we can use this and why we don't use a c. For a while when we were doing our indefinite integrals, we always wanted to make sure we included a c, a constant. So a couple of you guys have asked why we don't have it, and this is why. So if you do have a c value, our constant, we don't know what it is, we just know that it is just a number, no x's. And when we're using this fundamental theorem of calculus, when you plug in your b and then you plug in your a, we're subtracting. So when you do end up subtracting, your c's cancel out. So that's why you pretty much won't see this step anywhere written, because you know that your c's are just going to be eliminated. And here you go, you can see again, our fundamental theorem is when you plug in your upper bound and subtract plugging in your lower bound when you find the integral. So let's do an example or two to kind of refresh our brains, and then we're going to pull it over to our new idea. So here we go. We have an integral from 1 to 3 of 2x dx. So that just means that our variable we're working with and integrating with respect to is x. That's what the dx stands for. So here we go. So we have our integral from 1 to 3 of 2x dx. So when we're working with this, remember integrals, you're adding 1 to the exponent and dividing by the same value. So our integral is going to be 2x squared divided by 2. Now we need to put our bounds. We have from 1 to 3. You can simplify if you'd like. So this is really just x squared from 1 to 3. And now we're going to apply our fundamental theorem. So we're going to plug in 3 and subtract when we plug in 1. So we end up with 9 minus 1, which is h. And that's your answer. It's a number. It's not always a whole number, but it's a number. And that's the area under the curve between 1 and 3. So that's our good old-fashioned definite integrals. So again, just like with derivatives, there's going to be times where you have to either rewrite or you have to simplify a little bit first. So for instance, if I pull into number 7 here, and 8 actually, I would be rewriting both of these before I try to use my integral rules. For instance, with number 7, I would rewrite this as 3x to the negative 2 dx. Then I would continue my steps. So then continue. And I'm going to do the same thing for number 8. I need to rewrite this. I can't work with that square root, but I can work with an exponent. So this I would rewrite as 3x to the 1/2 dx. Then continue. So when you're working, just like with derivatives, you want to simplify where it kind of just looks like a polynomial. And then you can use your properties a little bit easier of adding 1 to your exponent and dividing by the same value. So last one I want to show you on here is a trig integral. And on this, you want to make sure that you're looking at your trig functions. I'll post a formula sheet on your Google Classroom just so now everything we know is in one spot. But when you're taking the integral of secant squared x dx, what you can remember is that what would have given us this as a derivative? And that's tangent. When you take the derivative of tangent, you get secant squared. So this is just general. This is one of your little rules here, that if you were to take the integral of secant squared, it's tangent. That's a rule. It's nothing you need to figure out on your own. That's something you can reference and use. So for instance, for this problem, we're going to have our integral is now going to be tangent of x. And we're going to be plugging in the values between 0 and pi over 4. We'll finish this one out because it's only a few more steps. So we have tangent of pi over 4 minus tangent of 0. You can use your unit circle or you can use your calculator for this. Tangent of pi over 4 is 1. Tangent of 0 is 0. So that means that our value here is 1. Okay? So using your integral rules, your integral formulas, you don't have to worry about remembering these. You can use your formula sheets and then you go from there. So here we are with our new idea for the week, which is our fundamental theorem of calculus, but part 2. So what you're going to notice is here, when we're working on problems, our upper and lower bounds are actually going to include variables now. So it looks a little bit tricky. It does look a little bit different, but what you'll notice is that here we have an x, or you'll have just a different variable. What you do is you take this variable and you're going to plug it into the function. These questions are going to be asking you to find the derivative of this integral. So what you can remember is that derivatives and integrals think of them like inverses. They can cancel each other out in a way. So that means that when we're taking the derivative of an integral, we're pretty much just left with this function, but we need to make sure that we're using the variable they're providing for us as our bound. So let's look at a couple examples where it's just from a value, a number, to a variable. So here we go. So down on the bottom of this left-hand side, I've already done one for you because it is that easy. So we're looking here, we're trying to find the derivative. You can see how the directions say find the derivative of this integral. So our integral starts from 0 and ends at x. That's a variable. So all we have to do is to plug that variable in. So x plus 2 is our solution. That's our answer here. You put a box around it, whatever you need to do to know that that's done. You just plug in x, or you plug in the variable they're asking you, and that's your answer. So looking at number 20, we have our integral from 8 to x of the cube root of t dt. And notice how the variable you have in your bound is not the variable you are taking the integral of. They should always be different. Most generally, you'll see a t here. So let's look at this problem together. So all we have is an x as our upper bound. So we're going to plug that in. So we have the cube root of x, and guess what? It's done. That's your answer. So that's when you have a variable as your upper bound. Sometimes we have a function as our upper bound, and that does get a little trickier. So I have a note for you guys. When you have a function as your upper bound, there's one additional little step you need to take. So the note that I have here is that when the upper bound is a function, not just a variable, you have to multiply the solution by the derivative of the upper bound. So think of this almost like the chain rule. When you have a function inside of another function, right? This is a composite function. Our chain rule always said that we would take the derivative of the outside with the original inside times the derivative of the inside. So bringing that back to this idea here, you can see that x cubed is a function. Pi over 2 is a number. Okay, it's just written in radical form, but that's a number. Rational, yeah. So we have x cubed. We're plugging x cubed into our function here, but x cubed is a function, so we need to multiply it by the derivative of the x cubed. You just want to clean it up a little bit. This final line I have written for you already, that's your answer. So it's very similar where you're plugging in that upper bound, but the one additional step you need to take is that you're multiplying by the derivative of x cubed, or multiplying it by the derivative of your upper bound. Let's do one more together. And you can see where this actually is still true for if it was just x. If I look over here at the ones that we've already done, our upper bound was x. So our derivative of x, right here, if we're looking, our upper bound is x, derivative of x is 1. So if I'm multiplying this by 1, it's the same thing. So you're plugging in that, and then you're multiplying by the derivative. So let's look at this final example. So we have sine of t squared dt. So when I'm plugging in my x cubed, I'm going to have sine of x cubed squared, because this was sine of t squared. I replaced t with x cubed, And then I'm also going to multiply this by the derivative of x cubed. So that's where this comes from. This is our derivative. Oops, I think I spelled that wrong. Let's go back here for a second. We'll just shorten it. d dx of x cubed. So again, simplify if you can. Don't go nuts with it. We can bring our 3x squared to the front. And then I can change this to just the sign of x to the 6. When you have a power to a power, you multiply. This is your final answer. So again, when there's a function, you multiply by the derivative when you're finding your final solution. If you have any questions, please go onto Google Classroom, join a Zoom, look at the helpful links in material, and reach out. Email me.